comes from somewhere, but I don't know where. That's what I installed on. But it was a nice, it was a good feeling. It's like that. Around the chest, like all aspects of it. Yes. I gotta go back and do that what you did just to understand it. Yeah, pretty much. It's like, I've got a crazy weird Yeah, pretty much did it. It's cool. Yeah, just yeah, so pretty much all I did was you implement the next and take it after that implement it next and everything that has next. So all I really do is just push to the next. So pretty much what I did was I was okay, it has the next, then talk about the issue. Something's on the same. So you get to the end of the day, you last all of this, essentially. Yeah. So then I said, well, there wasn't the next, what are we going to do? If that's less than this one, then this is just man, you can get the next page. So first you guys can be call. Yes, just on the page. So that took a little bit of the sequence again was just that's all. So that was like really nice. Yeah, I think that one a little bit. Yeah, because you had to add the table alias. So you get X and Y That's what I did. But other than that, it's just like Z this doesn't have all the stuff. Pretty much just set the first NP. Meaning there is the first NP. Right? And then you go through and the first NP. Right? So no, if you find that page, and then if not, if the first NP go ahead and replace that. And then if it comes in here again, another NP, it's no longer memorable. So you say, if you came out of here and this or it's not even the same as one, meaning that you have it on this file, we'll go ahead and read the page from it. And then we'll add it to the list, add that index. Otherwise, we'll just thanks for doing that PDF.
So in 125, let's get started. So in the last lecture, we talked about the very bottom layer of the database system, like we have the file pool and data, file space manager, right? File space manager. And today we'll talk about access methods and access paths. So this basically means, basically they are an interface for the upper level of your database to access these underlying files. So if you have a key file, then there will be an access method called key file because it provides a couple of interfaces for the upper level components to access the key, pages in the key file. Okay. So let's have an overview of the topic. So basically, we are adopting the external memory model, which is, as we talked before, we have an external disk, external memory like disk or SSD, which is much slower than memory. Then we have memory. So our processor only directly talks to the memory instead of talk to the disks. Whenever you want to operate on some data, you have to fetch that into the memory and do some modification, and potentially if you modify something, write it back to the disk. So let's have some, let's simplify things a little bit. So let's assume in the problem, basically, currently we are only talking about one single file. So whether it's a key file or other kind of file, basically in the file you have n items. Which are basically tuples. You can think of that as n tuples. Then in each disk block or in each disk page, you have 3 items. So that's to say, basically your items have fixed length, and in each of your page, you can only have b items at most. And we also assume the main memory. The size of main memory is M, which is in the unit of the number of items you have. So it's not bytes or pages. It's like you have in your memory you can store up to M tuples there. And we also assume for the questions, like for the problems we are talking about in this lecture, we assume the number of outputs is T. Okay. So that's to say, so suppose you do a scan, you have n output, right? You have n tuples at the output, then this T is just n. If you do like selecting half of those tuples, then it's 0.5 n, okay? And an I/O means moving a block or moving a page between the memory or disk. So that includes reading a page and writing a page, okay? And for convenience, we also assume m is greater than b squared. This, I won't talk about why we need this assumption for convenience. In this lecture, this will be mentioned over and over again in later lectures. Okay, this is just an assumption. Okay, so let's first see some fundamental blocks. So I think you should be very familiar with the left column of the internal memory operations like scanning things, sorting, permuting, and searching. So does anybody don't know why the boundary of internal memory operations happen this? Please raise your hand. You know. Okay. Yeah, if not, then I won't try to explain this. Right? Scanning is basically scanning everything, so that takes linear time. Sorting, the best case, the worst case best complexity of sorting is n log n, right? And when you do permuting, basically you're scanning through your array, then generate a random number each time to swap the current element with some element of itself or something behind it. Okay, so that's permuting, and searching is basically a binary search if you have a sorted array. Okay, so about the external part, things are different because your data, your tuples are stored in pages. So here we are only counting the IOs because the CPU cost is relatively small compared to the IO cost. So on the right column, so it's a little bit different here. Every number here is refers to the IO cost, the number of reads actually, or writes. So basically, scanning requires you to scan through every page, and for every page you are just reading the tuples in memory, so that doesn't count. Basically, the cost would be reading every page once, so that would be n over b. Okay, and sorting. If you do an employee merge sort, which we will talk after midterm, the time complexity is roughly like this: n over b log m over b and n over b. Okay, and for permuting, it's a little bit weird here. So there are actually two ways to do permuting in external memory. One way is to do the same thing as you do in main memory. Is that so you scan through all the items, and for each item so suppose for the ith item you generate random number between I to n minus 1. Then swap this element with that element. So this is guaranteed to have a random computation after you complete this scan. Okay, and that means for each operation you need to first you at least need to read every page once. Then if you are swapping this particular element with some other element in another page, then you need to read that page as well into the memory and swap them and write that page, the second page back to the external memory. Okay, so that means for every item potentially you could have one additional read here. So the time complexity would be, so if you have n items, you are paying n read and writes. And also you are reading the whole file again once. So that's going to attribute to n over b reads. So in total, it's actually, so it's not exactly n, I would say. This is the worst case would be n over b plus 2n. Okay, but this is the worst case. Still, even if this is just worst case, we were doing this worst case analysis, so this is of the same as ON instead of ON n over b. Okay, so that's why we have an n here. And what's this? This is just sorting. So this is the second way to do this. If your data is so large that this n is so large, you do not want to pay that many IO costs. What you can do is that you can generate one random floating point number for each of your items. Then sort the items according to that random floating point number. Then you get a random permute, right? So permuting in external memory is basically sorting. Yeah.
We're not comparing, we are just seeing how much cost is it for internal versus external.
Yeah. So you are basically only seeing the IO cost, and this is just to say if the other method is better than the first one, then you just choose another one. So that's why you take a mean here.
Okay.
Yeah. And for searching, so this bound is for B tree search. So if you have a B tree, then this is log B n. And if you don't understand that, it's fine. We are going to talk about like the next couple of lectures. Okay. So notice that the linear I/O cost is not O n, it's actually O n over b. Okay. Actually, in the sense of complexity, this actually doesn't matter because in a system b is always fixed. But in reality, because b is so large, typically b is like 200 or 1,000, right? For small tuples, you can go to like 1,000. Or for small tuples, large tuples, you still have like 100 or 50, right? So this will make a lot of difference.
What is B?
Okay, so B is the number of items in each of your page, the maximum number of items in each of your page. Okay, makes sense? So your page have a fixed size, okay, and your items also have a fixed size. So each of your block or each of your page can only store a fixed number of items. That's what the B is. Okay. Yeah. Right. And yeah, these nodes I won't go through them because all of these points we will go through them in the next couple of lectures. So just skip this. So let's do a warm up. How do we do queues? How do we implement queues and stacks in external memory? Right. So in internal memory, it's actually quite easy because like for a queue, you can just use a vector or like those array lists in Java, or you can just use a list, a linked list, right? Whenever you need to push something, you just put that to the list head. Then if you need to pop something, you remove something from the list head. Okay, that's how you do that in main memory. But when you do this in external memory, you no longer can do this in a naive way because otherwise, whenever you need to push something into your list, you need to read that particular page into the memory, then store that tuple in that page, then write that back. Okay. Then for each of these operations, you are paying essentially one IO cost. Two IO costs, right? So that's not going to work. The way you are going to do this is actually you have a buffer for both the queue head and queue tail. Okay, so you will have basically you are going to say this is a page, okay, and these are pages, pages and pages. So basically you are going to have a main memory buffer here. This is for the head, and this is for the tail. Okay. Whenever you need to push something, if there is still space in, suppose these are occupied and these are occupied. Okay. So suppose you have space in your head buffer, you push that into the in-memory portion, but it's still not on the disk yet. Once you fill this up, and you are going to push an additional item here, you write that back and empty out this buffer frame. Okay, you just write the complete block back to the disk, then create a new block which maps to the next block. Okay, so basically for every B items, you are only paying one item. So what's the cost for like inserting n items? That's only gonna be O n over B. Okay, right? And it's like you can have an amortized IO cost over B. Okay, and the same thing also goes with the tail frame. Basically, whenever you need to pop something, you pop that from the frame. Okay, once you have depleted this block, and you need to pop one other thing, you do not need to write this back. You still need to write this back. Okay, so that it's reflected on the disk. Then you read the next one into the memory, and it's filled. Then you pop the next item. Okay, the tail of that. Make sense? So still, if you are popping n items, the amortized cost is still O n over B. Okay, make sense?
So what if our queue expands over multiple blocks?
that's fine. Even if you span multiple blocks, you only keep the first block and the last block, yeah, in memory, and you don't only need that. The only tricky thing is that what if your queue is empty or only have one block? Then you need to know that you are actually accessing the same block. That's essentially as like in memory. So if you only have one block here, so if your queue only has one block, then basically these two you do not need two frames. You know this one block is the head and tail are all in this block. Then you need to have some special logic to handle that. Other than that, it's you only need to need two blocks. Exactly one for head, one for tail. Okay. And another thing is called stack. So, right. So how do you do stack? Stack is basically the same. You only need one buffer frame for the stack top. Okay. So suppose this is a page, and you basically keep this in memory. And whenever you need to push something, you push to the in-memory copy. If you need to pop something, you pop from that. And if it's filled and you need to push one more, you write that back and load the next one and load the empty one here. If you pop this until it's empty, you write that back and load the next one, this one, back to this buffer frame. Okay. So basically for stack, you can also do amortize the cost of O1 over B for one IO or O n over B for n. N push and pops. Okay, that's the IO cost. So yeah, that's about queues and stacks. Just a warm up to like show you how external data structures work. It's totally different from how you do with internal members. And so let's have a quick revision of the heap files. So heap files basically is a file that keeps track of blocks or pages of records on disk. So basically, the simplest heap file would be you just store the pages consecutively. Then for each page, it contains a header indicating the information of this page, like a slot array or something. Then you have this payload, right? In this payload, you store those records. Or you could have the slot array at the very bottom of that particular page. That's also fine. Okay. So basically, for the heap file, they are just blocks of records. And it must support the following interfaces, like scanning all the records, search for a record with a particular record ID. Remember, this is actually different from key search, because with key search, you need to actually access that record to find out whether the key satisfies your criteria. But for this, you can just remember how we define the record ID. It's basically a page number plus a slot number. So basically, you can just go to the page and fetch that particular slot. Then you get the tuple. So this is actually very efficient and something that heap file typically support. Search for a particular record ID. And of course, it needs to have capability to insert new records and delete old records. Okay. So these are the basically interfaces. So here we want to see what's the cost of them if you are doing this with heap file, okay, in external memory. And also there's a alternative file, a number of alternative file organizations. Like you could have heap file, which is unordered, as we talked before. You could also have sorted files. So a sorted file is basically still a heap file, but just except that it's sorted according to one of its keys. The key could be one column in your tuple or multiple columns. If it's multiple column, then it's sorted according to your lexicographical order. Okay. So basically, sorted file is no different from ordinary heap file, except that it's sorted by some key. Okay. And so if you try to find some record in your sorted file, according to a key. Suppose you want to find the key equal to 5 in the sorted file, you can do a binary search, right? But if you are doing some searching criteria that's different from the search key, like I want to do another key equal to 10, but this key is another key, is not the sort key of your sorted file, then it acts no different than no ordinary key file. You still need to scan everything and try to filter out those tuples that doesn't satisfy the conditions. Okay? And we will also talk about the cluster file and uncluster file. Basically, these are when you have a B-tree index, you will have the notion of cluster files and uncluster files. We'll talk about this later. So basically, currently we are just seeing, we're just looking at the key files and sorted files and compare what's their external memory operation cost. Okay. Yeah.
So to sort it, we do not have to have unique keys for sorting.
No, you do not need to have a unique key. You can have duplicate keys for like multiple items.
And then why does it say it has nothing to do with the concept of
Sorry, the concept of key. Right. So key basically requires this particular column is unique inside your table, right? It acts as some kind of like pointer. But here, a sorted file is basically if you want to access your data efficiently in some way, like you want to find all the persons with the GPA 4.0, then you need to have some way to search for them, and you want to do that efficiently. So that's why you sort that by the GPA. Okay? But it's definitely not a key because different people can have different GPAs. Okay?
I'm confused how this relates to our project. Are we going to be having to implement any of this?
Yes, you are going to implement the key file only, not the sorted file for this project one. For later projects, you are going to implement, I think, a unclassed key plus tree. So that's unclassed file. So that's about it. So just a reminder of this. So basically, as just a reminder of the notions we are using here, basically we have n items, and each block will contain at most b items. So each data block can only, the number of data blocks is n over b. Actually, there should be a ceiling, but for the simplicity, we can just ignore that for the purpose of complexity. Okay. And we have d. This d notion is actually not very correct. Not very accurate, because the average time to read or write a disk block can vary a lot, depending on whether you are doing sequential I/O or random I/O, right? So this d actually, I wouldn't recommend use this notion, but anyway, if you truly have an average for a workload, like your workload contains a mix of 40% of sequential I/O and 60% of random I/O, then you probably can still compute the average time to read or write this block. Then when you are doing analysis, if you just ignore the fact that different kinds of I/O patterns have different performance, then you can use this average time here. But in reality, I would suggest just look at only that is correct. So only the number of I/Os you are using is correct, but not the average time of your operation. Okay. So that's to say here the analysis here we make is only accurate about the number of I/Os we are making, instead of the time to do those I/Os. So even if that's the case, still this is actually still shows the trend of your operation. So you can still analyze the complexity. So basically, if something have a higher complexity, you can expect with larger data, it will eventually perform slower than the other with lower complexity. Okay? But the time would not be very accurate. We're just gonna show the general trend. So yeah, and we are also making some assumptions about our analysis on key file and sorted file. Basically, we assume we're inserting or deleting one single record. So unless we otherwise specify. And when we do equality selection, we are only selecting one, exactly one tuple, unless we say there are multiple tuples that satisfy the condition. And for key files, we always append the new tuple to the end of the file. Okay, you do not look for holes in your file. And for sorted file, you have two possible alternatives. One is you do not actually compact the file after deletion. So that means you are going to leave some holes in your file. And the other option is that whenever you delete something, you compact that hole. So basically, when you delete something that's a hole, you move everything just by one, 2 to 4, right? Then it's compacted. These are two possible alternatives of sorted file. Okay? And when we're doing selections, we are doing selections on the search key, so that the sorted file, we can use the sorting order of this sorted file to boost the search. Otherwise, the sorted file is no different than a key file. Okay, these are just the assumptions we make in class in this lecture, but in reality, it doesn't necessarily to hold. And also in your written assignments and exams, you cannot just assume that. You need to either write down your assumptions or we will make it explicit for you. Okay. So be careful about that if they appear in the exam. For example, if I give you a sorted file, it's on column A, but I say I want to select B equal to something, then this sorted file is no different than a key file. Okay. So remember that. Okay, so let's try to do some analysis. So we have 5 possible operations, very common operations of these two kinds of files. Basically, we can scan all the records in the file. We can do an equality search and a range search. So equality search is just something like you say where this particular column equal to say 5. And this range search is basically you say x is between, sorry, there's no is. X between 5 and 10. So that's to say, or you could write x greater than or equal to 5 and x smaller than or equal to 10. Okay, that's the same, that's the range search. And for insertion, unless we specify that, we are just inserting one particular tuple. And for deletion, we are just deleting one particular tuple. Okay. So let's see what's the cost of it. So for key file, it's straightforward. So if you are scanning all the records, you are just reading every block once. And for sorted file, it's the same, right? You still need to read everything once because you are scanning everything. So that's the I/O cost would be just N over B, right? You have N over B pages, then you read everything once. That's the scanning all the records. And for equality search, it's different. So for a key file, because everything is unsorted, so you do not know where that particular tuple is. So you need to first search for that particular tuple by by doing a sequential scan of the file. So that means, in the best case, if you are lucky, you basically just pay one I/O because the tuple could be just in the first page. But in the worst case, you are gonna scan every page once until you find that tuple happens to be in the very last page, right? So on average, if you assume it is equally likely you are going to search for something in your file, then the average case would be a half of N over TX. Okay. And for sorted file, you can do a binary search. Because this binary search is in memory, so basically you are binary searching for the page first. So if you have, say you have 3 pages here, you first look at the middle page, and in this middle page, you try to find whether the tuple you are trying to find is in this page. If it is in there, you're good, you find it, okay? But if it's not there, the tuple is, so suppose the key is 5, okay? So either this 5 is smaller than or equal to the first tuple here, or it's larger than or equal to the last tuple here. Okay? If that's the case, if this is the case, then you know this particular 5 will be only in the first on the pages on the left of this page. Okay? So then you can do a binary search over these pages. If this is the case, then you know this 5 is on some page on the right. Then you do a binary search on this, right? So after every IO, you basically have your search space. So that's why in total you have n over b pages, and you need to do log 2 n over log 2 n over b IOs to actually locate that particular page that contains the tuple you are searching for. Okay, and still the best case would be 1. And this is just something like if you think about general balanced binary tree, so binary search tree. So even if your best case is still one IO and your worst case is like this, but in the sense of complexity, if you take everything, take an average of everything, basically you end up with this. Maybe with some constant factor like 0.5, something that's near 0.5. But still, in the sense of complexity, it would be like this. Okay. So if you have a sorted file, this is much smaller than 0.5 n over b in general case, right? Because this is log, this is linear. Okay. And this is just for matching one record. So what if you have multiple records? Okay. So for key files, this time you cannot know whether you should end your search or not, right? Once you find one particular tuple, you do not know whether there's another. So you do not have a choice but to just scan the whole file once. So that's why you have n over b items here. Okay. And for sorted file, so basically you can try to find the first tuple that has this particular key. So say it's 5, then you do a binary search to find the smallest record ID that the tuple of that has this key 5. Okay. Then this is just log to n over b IOs to do the search. Then you are basically scanning that once because you have a t tuples that because this is sorted, so every tuples that have equal keys, they must be stored consecutively. So basically, you're gonna add a t over b here. Okay. So it's gonna be log 2 n over b for the search, then do a scan over all the matching tuples. So it's gonna be log 2 n over b plus t divided by b. In the best case, your first try will locate the lower bound of that particular key. Then you still need to do a t over b scan of all the matching tuples. Okay, make sense? Yep. Then the next one would be the range search. Remember, the range search is something like 1 smaller than or equal to x, smaller than equal to 10, something like that. Okay. So for key file, you still don't have any choice. You need to scan the whole file for every matching tuple, so that's still n over b. For sorted files, this is something similar to what you do in the equality search. Just the difference is that you do a binary search to locate the lower bound of your range search. Say this is 1, then you find the first record that has the key 1, search key 1. So that's the search cost, log 2 n over b, then plus the matching pages, number of matching pages, that's t over b here. Okay. So actually, this is actually the same as if you do an equality search over multiple matches. Okay. Then the next one will be insertion. So suppose, as we said, we have two alternatives for the sorted files. Suppose we do not do any compaction for the solid file. Okay. Then for key file, it's really simple. So if you are just inserting one tuple to the very end of that key file, you basically just read that the last page of this key file and put that tuple into that page and write it back. So that's 2 items. Remember, this is 2 items instead of 1 because you need to first read that last block into the memory, then store it, then write it back. So that's 1 read plus 1 write. But for sorted file, because you have to maintain the sort order, so you need to first do a search to find the correct location for insertion, right? You need to find the location where all the keys before that location is smaller than the key you are inserting, and all the keys after that location is greater than your insertion keys. This is the search cost. Then you only pay 1 IO to write it back. Why is that? Because you do not have any compaction. So you could have, typically, when you do not have compactions, we can assume the page you are looking at can have some kind of hole to fit that particular tuple in. Okay? So because you typically do not do compaction after a bunch of insertion and deletion, you could leave some holes in the middle. So when you search to that particular page, when you insert this tuple into it, you can directly just insert that in the memory and write it back. Then it's done. Okay? But of course, you can end up with some bad cases, like you are inserting things sequentially, consecutively, and in an increasing order. Then you basically have a bunch of pages that are full of tuples. You can have 1, 2, 3, 4, 5, and it's full. Then the next page is 6, 7, 8, 9, 10, right? And so on. So when you are doing this, still this is a no compact solid file. So when you are trying to say you are inserting an 8 here, then you need to move everything backwards. Okay? But in general, so when we are just analyze the cost for one particular insertion, we assume since this is a no compaction solid file, we will have some holes. Okay? Then what if it's a compacted solid file? Then every time when you insert something, it's the same as you do not have any holes in your no compaction solid file. Basically, you need to move everything after that particular key by 1, right? So that's why you have, in the worst case, you have an overhead cost because you might be just inserting the smallest item, then you need to move everything else. Or in the best case, you are just moving 1 because it's in the last page. Okay. On average, this part would be 0.5. Okay. So the cost would be log 2 and it will be plus 0.5. Okay. That's for insertion. And for deletion, so if this is a key file, you are trying to delete some tuple. But this tuple, you need to first do a search for it. Okay? Because this delete is something like delete some table and do a where x equal to 5. Okay? This x is not record ID, it's just some field in your tuples. Okay? Then you are going to pay a cost to first do an equality search for that particular tuple. So that's why you have a 0.5 and an unknown b here. It's the same as this one. Then you do an additional IO to write it back. Because once you locate that page, you have that in the memory, then you remove the tuple from the page in memory, then write it back. So that's why you have an additional 1 here. For the solid file, suppose you do not do any compaction on the solid file. So once you locate that tuple, you just remove that from the page, then write it back. You leave a hole there. Okay? So that's why you have a log 2 and number b for the search, then 1 for writing the page back. And finally, if you are doing compaction for the solid file, then it's the same as this one, right? Once you locate that particular tuple, sorry, this should be 0.5, and this should be 0.5. So on average, you are going to need to move half of your tuples. Then you are basically moving, like reading and writing half of your pages, right? Oh, yeah, sorry. There shouldn't be a 0.5 here. Why is that? Because when you are moving things, you are reading it once and writing it back once. So this is actually 0.5 times 2. Okay? So in the best case, this part will be 2, and in the best case, it will be 2. Sorry, I was wrong. And also that's also the case for this. So this is actually 0.5 times 2 would be that's the average case. And worst case would be 2 and number b. And best case would be 2. Right? Okay. Yeah. So that's about the order analysis here. So basically this table compares how costly the key file operations and sorted file operations are. Okay? And I would say this is a very important thing to mention, like you will appear in the exam, of course.
Can you go back 2 slides?
Yes, sure.
This one? Yeah. Okay. So best is 2.
Oh, sorry. I mean the second part of this. Basically, for insertion, you first pay the search cost, right? Then for the second part, the best case will be 2 IOs. The worst case will be 2 and number b IOs. Okay. Actually, this is not exact. Actually, you need to minus 1 as well. So this will be 1, and this will be 2 and sorry, 2 n over b minus 1, right? Because the first page is already in your buffer. But still, you can do this like off by 1 error is not an issue here because this complexity. Yeah.
Are we using blocks and pages interchangeably?
Right. Here, blocks are basically pages. Pages are blocks. They are the same. Okay. So yeah, when you're writing this, basically we're analyzing this in all notation. So off by 1 error is not an issue. Okay. But for this one is 2. I just put it here because in reality this is so small. When it's a constant, you do care how many IOs you have. Okay. But still, you can if you in the test if you write O 1, it's also perfectly fine. Okay. As long as it's a constant. Okay. So any questions? More questions about this part? The key file and solid file, the different cost of different operations. Okay, so let's continue. So yeah, let's talk about indexes. So basically, we have talked about what indexes are. Basically, sometimes we want to retrieve some records that satisfying some particular criteria, like using some of these fields. For example, you want to find all the students in the CS department. Let's just say basically if you have if you're the key of your there's an ID for your department, right? So suppose for your CS department the ID is 100, then you're basically doing equality search of PID equal to 100, right? And if you want to find all the students with a GPA greater than 3, then you do GPA greater than 3 in your web part, right? Sometimes you would do that. It's a quite common query issue in reality. So so one thing you could do is that you can have a sorted file of one of them, right? You can sort everything according to GPA. Then this one will be fast. This will only you only need to pay a log cost, log number of IOs to find all the students with GPA greater than 3. But then, since the file is already sorted on GPA, it's not necessarily be sorted on the DID, right? So when you want to try to find this DID equal to 100, then this sorted file is no different than a key file. Then you pay a linear scan cost. That's linear, that's n over b cost, right? So index is something that's auxiliary data structure that speeds up certain selection predicates. Like you can have an index in your key file with a GPA as its key, and another index with DID as its key. Okay, you can have two different indexes. Basically, you have an index here, index 1, that's on GPA, and you have an index 2, it's on DID, and they somehow point to your underlying key files. This is your key file. So when you do search, when you want to find all the students with a GPA greater than 3, you go to this index here. Then it will tell you which or what tuples in this key file satisfy this condition. Then you can directly just fetch those tuples you want. And if you are searching using a DID equal to 100, you go to this index, and it will tell you like how many of this, which of these tuples are satisfying this DID equal to 100. Okay. So basically, an index can boost your certain search queries. So remember the search key, this is the second time we mentioned this. Search key is not necessarily the same as the key because you can only have one key for one particular schema. But for a particular, here I should say schema, for a particular table, you can build multiple indexes of different search keys. Right? Yeah.
Yeah, and with database systems, does the system automatically generate indexes depending on what queries it sees?
Yeah, it depends on what system you are using. Right. So for example, for PostgreSQL, if you specify a unique or a primary key, it will have an index over that unique or primary keys. But other than that, you won't like automatically generate secondary indexes for it. Okay. But in certain systems, like especially in this era, we have a lot of cloud databases. They are trying to do some like auto indexing or auto tuning stuff, which will look at your workload and try to decide which search criteria is used more often. Then you will try to build an index in the background. Okay, so yeah, let's go back to the topic. So basically, for the indexes, an index is basically a collection. You can think of it as a collection of data entries. A data entry is basically, I would say, a pair of the key and one pointer or a set of pointers. Okay. So this is a data entry. Okay. So given a data entry k star, because this k star. So if you are given this data entry, you can just follow the pointer here. These pointers are actually just record IDs. So basically, what you do is that you have this k star. You follow this RID and go to the heap file and fetch the corresponding tuple out of that. So that's how this data entry works. Okay, but this is not the only way. So another way to do that would be you just embed that tuple inside the data, right? So that leads to like multiple ways of actually implementing this data entries. So there are actually at least 3 alternatives. So one is that basically you are storing a key and the tuple itself in the data entry. So one data entry here for the alternative 1. Sorry, this is alt 1. Okay. Basically, you have a key here, then you store the entire tuple with it in the data entry. Then each data entry will contain only one tuple. Okay, and right. Then once you have a data entry, you do not need to go to other files. You just return this tuple. Then it's fine. Okay. This is alternative 1, 2, 3, and alternative 2 would be. Basically, you still only have one matching tuple here in one data entry. You store a key, the key here, k, and you store an RID here, right? This RID serves as a pointer to a heap file. So this is a heap file, and this is a tuple with this particular RID. Okay. So once you have this data entry, you need to get this record ID out. Then you use this record ID to look up in the heap file for that particular tuple. Okay, this is the alternative 2. The third way to do that, because sometimes since you are not using the key, it's not necessarily unique. Then for one particular key, you can have multiple matching tuples. So in the first two options, basically you are going to have multiple data entries for one key. Okay, if your key is not unique. But for the third option, basically you are trying to store every possible matching keys, their RIDs in the data entry. So here is a key, and this is a list of RIDs. Okay, so there are basically multiple pointers into the heap file. Okay, basically you have multiple pointers into the heap file. Okay, so when you get one of these data entry, you can iterate through all the RIDs here and use those RIDs to fetch the corresponding tuples in the heap file. Okay, so these are. Remember, these three different alternatives are orthogonal to the organization of your indexing. Like you can have a tree index, you can have a hash index, but under the hood, index is basically a collection of data entries. So what format are you using for the data entries can be orthogonal to the design of the index itself. Okay, and so because you can have multiple indexes per file. This profile actually will be table. So or we can say this is called heap file. So it doesn't make sense if you maintain multiple heap files for one single table. You only need one because it's unordered. Two unordered files, even if they are stored in different orders, they don't make a difference to your requirements. So you only maintain one heap file for each table. So, but you could have multiple indexes for one file, just as the example we showed before. Like you could have a GPA index. You can also have a DID, like a department ID index. Then for each of these index, you can also choose different alternatives for this data entry. So, for example, you can have so suppose this is GPA and DID, right? For this one, you can have like alternative 2. Then for this one, you can use alternative 3. Right? You can have different choices. That's the one. Okay. Yep. So yeah. So for alternative 1, actually, so if your record is variable length, then that means your data entry is going to be variable length. So it's going to be a little bit harder for the index to actually store them because variable lengths are harder to deal with, like in a page. You need to have that smart array and whether do compaction or not, right? Stuff. But the good thing about this, once you get a data entry, you do not need to pay an additional I/O to actually get the particular tuple, right? Because the tuple is stored with the data entry. This is the best thing of alternative 1. For alternative 2 and 3, once you find the data entry and you want to get those matching tuples, you need to pay additional IOs because they are just RID pointers, right? So you need to pay. So for alternative 2, you need to pay one additional IO to go to the heap file to fetch the tuple. And for alternative 3, you have a list of RIDs. So potentially, say you have you have N matching RIDs there. Then you are going to pay N IOs to get those tuples out from the heap file. So, but the good thing about alternative 2 and 3 is that they are actually easier to maintain because if you change something in this, if you are like say you have a tuple here, this is a tuple, okay, and you have multiple fields, and originally this field is 2, then sometime you change that to 3. And none of your index is actually on this field. Then with alternative 2 or 3, you do not actually need to change the index themselves because the pointer are still valid. They still point to the correct tuple, right? But if you have alternative 1 and you still have 2 copies, you have a heap file and the index, and you are using alternative 1 for the index. Once you change this field here, you need to go to the index and actually change that corresponding field as well, right? To like make sure everything is make sure the integrity of the data, right? And with alternative 2, one good thing about that is fixed length. Typically, if your key is fixed length, of course, right? If your key, if key is fixed length, then this is fixed length, right? But for alternative 3, this even if your key is a fixed length, the entire data entry won't be fixed length because you can have a list of things which like different lists can have different lengths, of course, right? So in the alternative 3, you're guaranteed you are going to have variable length data entries, but in alternative 1, you still have a chance to have a fixed length alternative. So that's why sometimes we prefer 2 over 3 because of that, because fixed length entries are actually easier to handle in a data set. Yeah. And also for alternative 3, there's another problem is that this list can grow indefinitely. Like suppose your data is very, very skewed. Skewed means you have many records for one particular key, but very few for others. Like suppose you have 1 million tuples with a key 1, and you have 2 tuples with other keys. Then what's going to happen? If you use alternative 3, you are going to end up with 1 million a list with 1 million RIDs, right? Even if your RID only occupies like 4 bytes, 1 million such RIDs is going to cost you 4 million bytes. And that means this list could span multiple pages. It's not good for like maintaining an index because indexes are actually still organized in pages. Because indexes are still like you need to persist those indexes into the disk, so they are still organized in pages. So if you have a very long list that can span multiple pages, it's not going to be easy to do that. Typically, it poses a lot of like disk space management overhead to you. So typically, I wouldn't recommend alternative 3 for any cases because you could have a very skewed list. Yeah.
Even in alternative 2, what would we do if there are multiple records with the same key? We would replicate those, right?
Yes, you are going to replicate that key for multiple times, but that is actually fine for us for the purpose of space management because these keys can span multiple pages. So basically, you have the data entry for the same key, but different tuples in different pages. Then that's easier to handle because they are different data entries.
Right. But in this case, instead of like spanning multiple, like the same list spanning multiple things, there we'll have to have an internal search over the keys.
Right.
Right.
Yes. Correct. That's right. So if you have that problem, so actually you're gonna yeah, actually, let me answer you this way. So, if you are searching for like an equality search for one key, and you find that it's over multiple pages, then you don't have a choice. You need to read all of them, right? Because the correct semantics for that is to read all of them, right? So that actually doesn't matter. But the only thing that troubles is that if your key is really large, then you are basically duplicating this key multiple times. And we actually have different techniques for that. If your string is very large, if it is a string, and you use that as a key and it's large, then maybe they will not just embed that key into our data entry itself. It will actually contain a pointer to somewhere else, just like a string pool, something like that. Do you have?
I was just going to ask, where would the indexes be stored? Would they be stored in the same heap file as the table they relate to, or would there be a separate file that would contain indexes?
Yeah, typically it's in a different file than the heap file. It's going to be one file for each index or heap. Yeah. If you do have a questions? Okay. Yep. So about indexes, we have many things to like consider. Like, what's the typical form of your query? Is it like some field equal to or greater than or equal to some constant? Or is it some special search conditions like a range search? Or one-dimensional range search is actually simple, right? It's just the AND of two, the field of constant, right? Range search. But if it's two-dimensional, it's actually a little bit different, right? It's actually, so basically, if your data is two-dimensional, so suppose you have a table that has x and y as the coordinates, then suppose this is on a plane, right? So you have a bunch of points. These tuples correspond to these points, and you want to do a range search. You want to draw a rectangle here, right? This is a possible two-dimensional range. This is actually easy because you can just specify like this is x mean and x max. Then your x should be between this x mean and x max, and y is between y mean and y max, right? Rectangular. So this axis parallel rectangular region is easy, but sometimes you do some very strange regions, like you want to do a circle, like you want to search for a circle. This is called what is it called? Like distance search, something like that, right? You want to find all the points that's within certain distance to one point. Okay, then probably this ordinary index structure will work, right? And also sometimes you can have you can search for the k nearest neighbors. Okay, that's to say you look at all the pairs. All the points. Look at the distance of all the points to this particular point. Then you compute the distance between them, and you try to find the top k of them. Smallest k of them. Then it's a k nearest neighbors. So we have different kinds of index structures for all. So a lot of these different search criteria. So this is actually a very wide research area, which is, I think, is the spatial parts. Yeah. And if you look at the top conference like Sigma, you will find there's actually a particular track that focuses on this kind of problems, like spatial problems or spatial temporal problems. Yeah. So we won't talk about these spatial indexes in this course because they are much more involved than ordinary index structures. But if you are interested, you know there's something called R tree. It's very common. There are KD trees, and there are some other stuff. I don't remember the name, but if you are interested, you can look up those stuff. Yeah, and in PostgreSQL, actually, there's a geospatial index structure. I don't remember the name, but if you're interested, you can look up the documentation. Okay. So in this course, basically, we're going to focus on tree index and hash index. So for tree index, it can basically support all of this. But for hash index, it's just equality search. Okay, that's the difference between tree and hash index. Okay. And also, apart from what kind of operation an index can support, we have different questions to ask, like how do we represent the data entries in the index? That's the three alternatives we've talked about. And whether it's tree-based or hash-based. And there's the notion of primary versus secondary. So basically, primary index is an index that's on your primary key. So that means the search key matches your primary key. A secondary index is something other than that. And you could have cluster index and uncluster index, right? So we will talk about this just in a minute. And you can have single key and composite keys. Yeah, talk about this first. So I won't go through this B tree and hash here because we will mention that in the coming lectures. So if you don't mind, I'll just skip these few pages. But if you look at the B tree, it's basically a tree, of course. And it's different from a binary tree in that each of its nodes have multiple links to have multiple children, okay? And everything in one node, so basically in one node you have multiple keys, and these keys are sorted. So and between each of these keys, every two of these adjacent keys, you have a pointer to a child page, and it's guaranteed everything in this child page, its key is between the corresponding two keys in its pair. Okay, so basically, if you have a 5 here and 10 here, and you have a link here, so you know everything here is between 5 and 10. That's basically what we treat. And yeah, I won't talk about details. It's an example. Okay, so basically, one thing to know about B tree is that so every node is sorted, and you know on one level. So on level, one level means every node that have the same height in this B tree. So this has a height 0, and something that is child of height 0 node is height 1. Then basically the data page has a height of h. H is the height of the entire tree. Okay. And of course the last level are data entries. So the data pages only contain the data entries. So one thing about B tree is that the keys in each level is actually sorted. So if you add links between nodes in one level, so suppose if you add a next link here, you link every node in this one level as a linked list. Everything here is actually sorted, right? Why is that? Because everything here is between, is smaller than this 17, right? And everything here is greater than this 17. So that means everything here is smaller than everything here, right? And so on and so forth. And that gives us immediate conclusion that everything in the last level is actually sorted, right? The data entries are actually sorted in the B tree. This is a very important property to use there. And another thing is called hash-based index. So I think you might all be familiar with hash tables, right? Hash tables or hash maps. So basically, that's every time you want to insert something or delete something or look up something, you first compute mapping from your key to a hash function, to a hash value using a hash function. So hash is basically n to 1 mapping. N to 1 mapping. This is a hash function, right? So basically, whenever you are given a key, it's guaranteed to, so the same key will map to the same hash function, right? That's what it's saying. So if you give it a 1, it's going to be mapped to some, say, 5. Then 2 could also map to 5. Then, but if you give it 2 tuples that all have a key of 1, it will all map to the same hash function, right? That's the hash function. So in hash table, it's easy. In memory, you have open open hash or closed hash, right? You can have like each of your bucket, like each bucket corresponds to a hash value. Each bucket can have only one value, or it can be simply a linked list, right? When you are inserting things, when you have a collision, if it's a closed hash, then you just add something to that list. If it's an open hash, you search for the next available empty slot. That's in memory hash thing. But for external memory, actually, the hash index needs to be organized in terms of pages. So actually here what we do is that for each of this bucket, instead of like a single value or a linked list, we're basically using one page or a bunch of pages, right? So for suppose this is a hash table, and your range is 0, 1, 2, 3, right? So basically, you are allocating one entire page for each of these buckets. And when you do this hash, you put that tuple into the corresponding page. And if it is full, basically you can create an additional page and link to that. Okay, that's one way to do that. So this is actually called static hashing. So suppose you have a fixed range of your hash function, then basically here you will create one page for each of this bucket. Then you will store the tuples in those pages. Then if you have overflows, then you do an overflow page. Then you have a link there. Then additional tuples with hash key 1 will be stored here. Then if that's full, then you create another one, and so on and so forth. Okay, this is hash index. So yeah, this is just an illustration, so don't mind of that. So we will talk about more hashing techniques in database later. And we've talked about this primary key versus primary index versus secondary index. If the index is on primary key, then it's primary, otherwise it's secondary. Okay. Yeah, I wouldn't say that search key contains primary key. That's a little bit odd to me because if your primary key is, say, your primary column is x, and you have an index over yx, you actually cannot search for that primary key for a very obvious reason. I'll just talk about this in a second. So if you are using this composite search key, the order you search that is a lexicographical order, right? So suppose your x is your primary key, and y is something else. And you have an index over y and x, right? So the way you compare two things like y1, x1, and y2, x2, is that you first compare y1 and y2, right? If y1 is smaller than y2, then this is smaller than that. The first one is smaller than the second one. If they equal, then you compare x1 and x2, right? So suppose you have an index over y and x, and you want to search for something x equal to 5. Can you do that? Actually, you can't. You cannot specify that using one single range code, right? You cannot write, say, yx like equal to what should you put here, right? Doesn't make sense. So in reality, if this is a B tree, remember the data entries are all sorted in the last level, right? So basically, you're going to have 1, 5, 1, 6. Then you will have 2, 5, 2, 6, 3, 5, 3, 6. Right? Then everything that with x equal to 5 will be scattered around in your data entry level. Right? So if you have a composite search key like this, you can only search a range query for the first field or a prefix of your fields, but not a suffix or any other combinations. Right? That's the key point of this. So I don't think this definition makes too much sense to me here. So if a search key contains the primary key, well, if this is the case, this is the key, then it's not usable as an index for searching for the primary key. Right? Okay. So I would say it's just like if the search key is just the primary key, then it's called a primary key. That's how typically a database is defining this. And something is called a unique index. As its name suggests, it basically means that the search key is one of your candidate key specified using this unique keyword. Okay, that's called unique index. Okay. And yeah, let's talk about cluster versus unclustered. So remember, these two terms actually makes more sense for B trees. I don't think for hash indexes it would make sense to say this is cluster or unclustered. But maybe not. Maybe I'm wrong. But I would say let's see this in the sense of B trees. So remember, the data entries are sorted in the last level, right? In a B tree, it looks like this. So this is a tree, and these are data entries, and they are sorted, right? And suppose you do not use alternative 1, you use alternative 2 or 3. So how do you store things in your heap file? This is your heap file. So for cluster index, actually you store the tuples in the same order as your index. That's to say, basically this pointer is going to point here, 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 like this. So basically the data entries are stored in the same order as the tuples. Then this is called a cluster index. Then if this does not apply to your index, then it's an unclustered index. Okay? Why this matters in this case? So basically that means, so suppose you are doing a range search of your B tree, and you have identified this part matches this part is something you want to fetch, okay? And you have a bunch of pointers. If the tuples are stored in the same order as these pointers, then basically you can do a sequential scan of things, right? Then you only need to pay how many? Like suppose you have T matching tuples, you only need to pay T over B IOs to get everything out, right? But if it's this case, if it's an unclustered index and this is your matching range, and you have a bunch of RIDs, right? And there are T such RIDs, and you need to actually pay 1 IO for each of these tuple, right? So because why is that? Because for the first tuple here, you need to go to this page. Then for the second tuple, it's not on the same page, so you need to fetch that page as well, right? So for each of these links, most likely you are going to pay 1 IO. So in that sense, the cost for fetching the tuples themselves is going to be T instead of T over B, right? So this actually makes a lot of difference. And also, because this is sequential, this is random. Remember, sequential IO is at least 20 times faster than random. So that means not only you are paying much more IO cost, you are essentially doing a much slower IOs than this one. So the end result will be a very huge difference. For example, I did this example. So I built a cluster index in single server over a table of how many? I don't remember how many, like a billion or 100 million tuples, about 100 million tuples. And I have a cluster index. So the time for scanning the whole index is only like 2 minutes. But if you use the unclustered index, it doesn't finish in like 7 hours. That's the difference. To this date, I still don't know how much time I spent on like scanning the unclustered index. It's really, really bad. So in reality, this actually makes too much difference. So sometimes even if you have an unclustered index on some particular key, but you know you are matching a lot of tuples, then typically it's better to use unclustered index to do a full table scan instead of like using that unclustered index. That's the I would say takeaway message for this part. Okay, so that's clustered and unclustered. And another thing to say is that, so we just ignore the alternative 1. So basically alternative 1 just implies it's clustered because like it's directly in the data entry. Of course, it's in the same one. So yeah, that's that. Okay, so a cluster file is actually a special kind of index. It's basically a cluster index with an alternative 1. Let's just say you are basically combining the heap file with the index. Why is that? Because you are directly storing the tuples inside the data entries. So you do not need to store a second copy of those in a separate heap file. You can directly access those data entries for those tuples. Right? whenever you want to do a scan, just scan those data entries.
How is that different from a sorted file?
How is that different from a sorted file? Yes. So for a sorted file, remember when we want to insert something, we could end up moving a lot of things, right? But for a B tree, you only need to pay a log cost for no matter where you insert. That's it. Yeah. So yeah, we will talk about this occupancy term a little bit later when we talk about B tree. Okay. So don't worry about that. Yeah. So that concludes this lecture. So basically, we'll talk about different access methods like key file, solid file, class index, class index, class files, right? And so we have different kind of like core conditions so that we could use different kinds of indexes. Okay. So this concludes this lecture. And for later lectures, for next lecture, we'll talk about tree index, and for the next maybe the coming weeks, we're also going to talk about hash index. Then we will end there. So basically, the midterm will cover everything up to hash index. Okay. See you next time.
See you.
Yeah.